Hello folks, I'm gonna solve this problem here. We are asked to find the electric field at point A due to these three charges. First of all, I'm gonna name these charges as Q1, Q2, Q3 so it can be more instructive. So let's call this guy Q1, this guy Q2, and Q3. And as we know, electric field is always away from positive charges and towards the negative charges. We're going to use this idea to show the direction of electric field due to each electric field point A by Q1. We have the line combined 2 points already. It will be away from that line, so E1 will be to the right here. Let me pick a color. So it should be fine. Here's our E1 to the right. Let's pick another color for E2. E2 is Q2 is a negative charge, so E2 will be towards it. So the electric field line, let me pick a line here to make a better job there. Electric field due to E2 will be towards Q2. Due to Q2 will be towards itself because it's a negative charge. So here is our E2. And Q3 will apply an electric field downward because again it's a positive charge and electric field will be away from the charge. So E3 will be down here. Let's represent that here. The lengths are not representative here, just the directions I am showing, and we'll find the magnitudes. Let me redo that. So this is E3. We're gonna set up an XY coordinates right in here. The point of interest will be the origin, so I'm gonna set up Y such that this is Y coordinate and X will be along E1 here. So to the right is positive X, up is positive Y, down will be negative Y, and left will be negative X. We will need to find components of E2 here. E1 is only along X, will be easy, only X component, and E3 is only along Y. But for E2 we need to find its components X and Y. For that we draw lines, perpendicular lines to X and Y coordinates where they hit the coordinates. We draw line joining origin to that point where it hits. That's the components. This will be then Y component and that will be X component. To try to do a better job here, drawing line downward. This is a better looking one. So this will be E2, Y direction is positive upward, and E2 X to the left, so direction is left negative. Now we're going to calculate these magnitudes of these electric fields, components of E2, and for that we'll need this angle here. We will also need the distances for each. Charge 1 has distance to point A, we'll call that R1. That's a known distance, 2 centimeters. Charge 2 will have this diagonal distance, R2. We'll calculate that using this triangle here, which is a right triangle. We have 90 degree there. And we also calculate this angle alpha using this triangle. And charge 3 has a distance R3 over here. It's also known as 1 centimeters. So the values we know, R1 is equal to 2 centimeters. We convert to meters right away, 0.02 meters. R2, we will calculate using this triangle here. It will be one corner, perpendicular corner squared plus the other in square root. It will be 1 centimeter squared plus 2 centimeters squared. And if we do this, this is Pythagorean again. Always one perpendicular side squared plus the other perpendicular side squared is equal to hypotenuse squared. That's what we're using here. If we do this calculations, R2 will be 2.24 centimeters. And that's equal to 0.0224. I'm not going to round here, just leave the full number in meters. And R3 we also know 1 centimeters, 0.01 meters. Charges are given in coulomb. We convert in nanocoulomb, sorry, we convert to coulomb. Q1 is minus 10 nanocoulomb, minus 10 times 10 to minus 9 coulomb. Q2 is, sorry, Q1 is plus, Q2 is minus 10 nanocoulomb. That's also minus 10 to minus 9 coulomb. Remember, we always use SI units, and coulomb is for SI units. And Q3 is 5 times 10 to minus 9 coulomb. Alpha value we can find using tangent. Tangent alpha would be opposite over adjacent, so 1 over 2. We can use that information to get alpha. Alpha will be tangent to minus 1 over 2. And once we do that, we'll find the alpha as 26.57 degrees. Now we have everything we need to solve this problem. We'll apply the equations. Energy, electric field for E1. Let's start with E1. K Q1 over R1 squared. Again, we look at the magnitudes of the charges. K is our electrostatic constant, or Coulomb constant. It's 9 times 10 to 9 Newton meter squared over Coulomb squared. Q1 is this charge here, 10 nanocoulomb. We put the Coulomb value, 10 times 10 to minus 9 coulomb. That's divided by R1 squared, 2 centimeters, 0.02 meters squared. Result will be Newton per coulomb. And the value we find from there should be, let me find that value. I should have somewhere here. A3, A1, sorry, should be 2.25 times 10 to 5 Newton per coulomb. With similar approach, we will find E2 and E3. E2 would be calculated with Q2 on R2, and E3 with Q3 and R3. I'll just put the equations, and I'll give you the results. Make sure you guys calculate and find those. K Q2 over R2 squared. We find R2 value here, 0.224 meters. When we put the values, we'll find that E2 as, let me see what value here, 1.79 times 10 to 5 Newton per coulomb. And similarly, E3 will be K Q3 over R3 squared, of course, and the value should come out as 4.5 times 10 to 6 I'll put this in 10 to 5 format. 45 times 10 to 5 per coulomb. After we find all these values, we have to redo this better. We have to find their components. E1 is only along x, so E1x is positive, it's equal to itself, so it's 2.25 times 10 to 5 Newton per coulomb. E1y is 0. E2x and y we have to find. E2x will be E2 times cosine alpha, which is this angle there, 26.57 degree, and that should give us a value of let's see, 1.6 times 10 to 5 Newton per coulomb, and that will be negative because we already defined that E2x is negative. You can put it here or just put it aside. Know that you'll have to take that value as negative, so it's up to you to decide. Either just put it in front of the number. Either case, you have to take E2x as negative. E2y is also negative. Sorry, that's positive, not negative. And it will be E2 sine alpha, which is 26.57 again, and that should give us a value of 0.8 times 10 to 5 Newton per coulomb. E3 is only along y, it's negative, so E3y is equal to E3 itself and it's equal to E3 4.5 times 10 to 6 or 45 times 10 to 5 Newton per coulomb. It's negative and E3x is 0. Using these, we will calculate I'm going to delete this part a little bit here. I'm going to cut it a bit because we won't have space. We will calculate E total now. E total x is equal to E1x plus E2x plus E3x. We add them, of course, as vectors. So minus plus we'll take into account, and from there we should find E total x to be equal to let's see here 0.65 times 10 to 5. Newton per coulomb. E total y will be addition of all y's, E1y plus E2y plus E3y again as vectors, so plus minus should be taken into account, and that should give us a value as minus 3.7 times 10 to 5 Newton per coulomb. And then we find the total electric field as we always do, E total x squared plus E total y squared in square root, and that will be equal to 3.75 times 10 to 5 Newton per coulomb. You can guess that E total will be somewhere along there. Let's also show that with a yellow line. Because we found positive x and negative y, a component is significantly larger than x. It will be something like this. Carry this a little bit down. can manage. I can also find the angle it makes. This will be IE total. This is just representative, of course. It will make an angle theta with the x-axis here, and I can find an angle theta. As always we do, theta will be equal to tangent to -1 e total y squared, sorry, not squared, e total y over e total x. This is kind of a long question. Again, on the harder end, I took a lot of space here, but that's all. If you can understand this question, you can get any question in terms of solving adding vectors, including electric field, electric force, and so on.